talking about something called the Gauss map, the Rodriguez-Gauss map. It simply says that if you have, a manifold, something like that, and you pick a point from it, then you can assign a normal vector to it. I can assign a normal vector. So I can take any point and I can assign a normal vector. What do you mean by assigning normal vectors? Another way to, and if you can do it, for example, all over the surface, what does it really mean physically? Physically, this really means that this surface is orientable. And what do you mean by being orientable? So when something is orientable, in other words, something is orientable roughly if you can say that it has inside and outside actually. Okay? So if I have a circle, I can say that there is inside and outside to the circle. Sphere, inside and outside to the circle. So similarly I can, for the torus I can say inside and outside of circle. Slender, inside, outside circle.
Interior, exterior case?
Not a topological interior, exterior, but in other words, you can. So in other words, we must be able to draw the normal vectors in the outward directions. But we'll be able to draw the normal vectors in the outward directions if there is something like outward. Okay. For example, if you take the Mobius strip, okay, that's not orientable. Okay, it's a non-orientable manifold. Why? Because there is no inside and outside. Okay, so if you call something inside, then the same thing becomes outside as you travel around it. Okay. So when I'm saying that, I'll be able to draw the normals on entire surface, what essentially it means is that there is inside and outside to the surface. And what is Rodriguez map? In other words, since you can draw or assign a normal vector to the entire surface, so I can treat this normal vector as a map from this surface or manifold that you have into S2. Okay? So in other words, I can treat N as a map that takes a point P and throws it on a sphere. So it throws it on a sphere somewhere here. This will be what you call N of P. Are you getting the point? I know that if N of P is a point on a sphere, then this point is going to have a unit distance from origin, and that's what precisely it means, because we know that if I take the point and draw a normal vector, that normal vector is of the unit, how do you call length actually. So I'm saying that let's collect all unit vectors that you have. I'll treat N as a map actually that takes a point from the surface and gives you what is called the unit vector. So yesterday we also talked about that. Imagine if your surface is a plane, okay, and you take an arbitrary point from the plane and you draw a normal vector. In other words, you throw it on, what do you say, on sphere. You get this one? So it's like throwing this point on sphere is same as drawing a normal vector. Okay? Now on plane you can have two principal directions. You can have essentially two principal directions. Horizontal and vertical one. And now what I would like to do, that what if I move on these principal directions, okay, with this normal vector, what kind of behavior you're going to get at? In other words, if I move from this point to this point, the unit normal vector would be same. And this would be same. Are you getting the point? Since the curvature is 0. In fact, you take any point and draw a normal vector, it would be parallel to all these vectors. Are you getting the point? So in other words, all these normal vectors are not different things, it's just the one normal vector, okay, that you are basically getting, because all these are parallel to each other and have the unit length. So no matter what point you take. So when you throw, okay, you know, all these points, entire points, into the sphere, what are you going to get?
Straight lines.
You will basically get one point actually, because all of the normal, you know, vectors are parallel to each other. They are indistinguishable. There is no difference between this point, normal vector at this point, or the normal vector at this point actually. So all of these are basically mapped onto the, you know, one and the same point. Think about it, because if I change the point, in other words, if I take in a strip actually, okay, and I, you know, taking, for example, another point, so this point is going to have a pre-image here, somewhere here, okay. Now this point is different from this point actually. So in other words, on the pre-image, normals are going to have the different directions. If you are moving, you know, on this line here. But the question is that here, none of the normals have the different directions. All have the same direction. So in other words, you are not moving at all. You are stuck to a point. So everything collapses to basically one point. So that's one of a way to make sense of it. So if this happens, we're gonna so this would be something interesting. What is the next thing? Okay, let's take the same map, but let's talk about the sphere actually. So we talked about the sphere yesterday. We talked about the sphere yesterday too. Imagine that you have a sphere of radius A. Okay. And so this is your surface, and this is your sphere on which you are mapping everything. Okay? And then I'm saying that, okay, take a patch or maybe a closed circle on this point, and I would like to just see that how this circle, the points within circle are mapped onto the normal vector. Onto the, you know, S2 under this map as n. Are you getting the point? Okay. So if I take a point here, so for the sake of simplicity, just take 4 points. So we take A, for example, B and C and D, and take 4 points. How does the normal vector on this point is going to look like? So maybe something like that. On this point, maybe something like that. Think about it. So if you have a sphere and you put a normal vector, you change a point, then, you know, direction will change. Are you getting the point? Okay. So if I am here, okay, I'm going to be mapped onto a point, maybe somewhere there. Okay. So I can take this entire strip or maybe this ball, and I can map it onto, you know, what do you call the S2, and I'm going to get something like similar on S2. So the only thing that I would like to basically make sense of it, that when I am moving the normal vector along this curve, or even within this basically circle, at any point in the circle, what impact it is going to make on, what do you call this circle actually, or this patch onto the N2 sphere. So if I take this point, okay, and draw a normal vector, something like that, this is equivalent to saying that take this point and throw it onto the sphere. So where it is going to be? So it's going to be somewhere, maybe here actually.
सर सेम जगह पे है ना?
I'm sorry.
जैसे ये सर्कल है उसी तरह उसी सर्कल
होगा उसी okay. It is going to be, a similar kind of a circle. In case of sphere, is going to be almost at a similar kind of location, but the difference is going to be the size is going to be different. Maybe since this is a unit sphere, say with the radius a, and that's a unit sphere. Okay, so maybe we can have a bigger and a smaller chunk of the piece, but it's going to be ultimately the same. Okay. Now, if I am moving, the normal vector along these points, like this is strip and I'm going to reach from A to B, what's going to happen? As an images. In other words, if I select this strip of point and apply N on it, what you're going to expect to have actually? So you're going to have something similar actually. So the same arc actually. Okay. So in other words, the way you are moving, your normal vector is changing, on this, what do you call part of the sphere, this small chunk. You can have the same kind of orientation here. You will have a similar kind of a circle drawn here actually, on which all these points are going to be mapped. Is it making sense?
सर ये यूनिट स्क्वायर पे हमारे पॉइंट्स हैं उसकी प्री इमेज हमारे पूरा प्लेन है
नहीं उसके
प्लेन प्लेन कैसे
we can't say it's not okay. Tangent plane is going to play a role. In other words, when I'm saying that I am computing the changes in the normal vector, basically that is going to give rise to the tangent plane, which I'm going to talk very soon. But what I just want to basically tell you that whatever however the normal vectors are moving on this circle is going to produce. When I'm saying that normal vector is moving on the circle, in other words that I'm mapping these points onto the sphere actually. Because think about it. You change the point and draw a normal vector here. So that normal vector can be treated, or n of the p can be treated as a point on this sphere actually. Okay. The way normal vector is changing here is going to produce a similar kind of a patch here. But the only difference is going to be that it could be scaled up and scaled down and nothing else. Is it making sense? So if this happens, so in other words, orientation, so it's like if you are moving positively here, you observe roughly a positive movement here, you're going to say this object has a positive curvature. Okay, so this object has a positive curvature. Let me give you another example from which you can, somehow. So let's consider a saddle. So what's a saddle? So the seat on which they sit actually in the horseman, it's a kind of a saddle. Okay, so it's going to be something like that. It's difficult to draw, but let me try. Okay, so maybe I must draw it more deeper. Okay. Okay. Can you see it? What the heck is going like a saddle? By the way, what will be the principal directions here? So there will be two kind of principal directions. Huh? So not the horizontal one, but like So in other words, so when I am moving this way onto the circle, so onto the point, it's like I'm going down. Okay. So that's one of the principal directions. lines which are parallel to this basis throughout the surface on the both sides. Okay, so that's one principal direction. What would be the other principal direction? That's like moving on this way, roughly like a semicircle. It's a subtle, but you are moving on this way. That would be another kind of a maybe the principal direction. Okay? And I'm saying that now take a point, any point, okay, and draw a circle on this actually. Okay? Let's draw a circle on it. So how does the circle is going to look like? Okay. So something like that. Something like that. So you may assume that this is onto the top of the back actually. Okay? So some part of the circle is on the other side. And some part of the circle is on this side actually. Are you getting the point? So it's like, okay, take a circle and twist it actually. Take it, fold kar diya. Pringle ki tarah kar diya. Let's assume it like that. Are you getting the point? Okay. Now, on this circle, if I am moving this way, it's like I am going down into the valley. Isn't it? As I am.
Yes, sir.
If I am moving in this direction onto the circle, so it's like I am moving, down into the valley. But if I am going this way onto the circle and crossing through this point, it's like what? It's like I am going over top of something actually. It's like a top of a half cylinder actually. Think about it. I guess it's pretty important to visualize it. Is it making sense? And now I'm saying take 4 points on the circle. So let's take a point A, maybe a point B, and maybe a point D here. How does the normal is going to look like? On this side, this is going to be like that actually. Okay? And here it's going to be above actually. And similarly here. And on that side is going to go outside actually. Are you getting the point? You take a circle. And I'm saying that now throw all these points of this circle, okay, onto the sphere through the Gauss map. Okay? And let's see what you get. Okay. So this point would be mapped where? So A would be mapped where? So it's going to be mapped onto some point where the normal vector is similar. In this manner. Are you getting the point? So maybe this is the A point. Okay. So in other words, I'm saying now take the same circle and put it on the top of a sphere actually. So what you're going to have? You're going to have some points on the other side and some points on this side and so on and so forth. So A is the point where you mapped it, but you mapped it in such a way that the normal vector is outward. How does the B is going to look like? Maybe this is B, C, and this is point D. Are you getting the point? Okay. How does it going to look like? So maybe B is somewhere here, okay, and C is somewhere here, and D is going to be somewhere on the other side. And so if you map these points, you're going to get a circle. But I would like to.
सर ये लाजमी सर्कल ही होगा स्फीयर पर.
Okay, it's going to be some kind of patch. Obviously, even this is not a circle. So it's just a patch actually. But if this patch is a closed patch, it will be mapped to a closed patch. Okay? Essentially, okay, you can abstractly assume that if your normal is moving, that if you are computing the change in the normal in one orientation, okay, like okay, say for example, positively, you're gonna say that you're gonna have a movement of the points negatively. So you're gonna have an opposite movement, and that's a sign that the surface has a negative curvature. It's unlike the sphere. The way you are moving here, you are moving the same way here. So that's a sign that, while if this is happening, so the curvature is zero. So that's an example where the curvature is positive actually. And here you are sitting on a curvature negative, okay? So which things are going to have a positive curvatures? For example, it's like if you take a bowl, think about a bowl actually, और उसे उलट करके रखते हैं, okay? So it's gonna have a positive curvature. But उसको सीधा करके रखते हैं, so it's gonna have a negative curvature. And you take a sphere, you're gonna have positive curvature. Sorry, zero curvature. Now, based on this observation, what I want, think about the torus actually. The torus is a pretty complicated example. Think about it. Torus is a pretty complicated example in the sense that on this surface there are parts which have positive curvature and there are parts which have negative curvature and there are parts which have no curvature actually. So can you identify the parts, for example, just by looking here that which of the part doesn't have any curvature? Which part? For example, if you take the top circle, there will be no change in the direction of the normals actually. Absolutely. So can you think of any other part than this actually? So if I draw a circle, no, they will be changing. The downward is different. So this above part of all parts on the top or the bottom of the torus are basically what you call the parabolic points actually, roughly. We're going to talk about it soon. So that has no curvature. How about the part that has a positive curvature? So this outer part actually, the outer part. Okay. So it's like you take the donut and cut into the pieces. Okay. So this outer part. So if I cut this donut, slice it. Okay. Then this outer part is like the bowl actually. Isn't it? The outer part. Donut cut करके if I put it half of the donut, okay, in this manner, okay. So what's going to happen? So it's like the outer part, the above part is like a bowl, okay. So that part, in other words, this part is going to have a positive curvature. So you're going to have also a positive curvature if you go this way. So in other words, if you slice it in this way, you can बजाय इसके slice it in this way. What if I slice it in this way? So you're going to have a two disc section. Okay? Now that's also like what do you call? Okay? Like a bowl actually. So you're going to have a positive curvature. So this outer part so the top and the bottom parabolic point, no curvature. So this outer part of the tube has positive curvature. Okay? And what would be the part of the negative curvature? That's the inner side actually. Think about it. Okay? That's the inner side. The inner side. Okay? Are you getting the point? Take it. So what you can see is that this is a pretty, so maybe we are kind of living in a universe which is like that. Sometimes which has a positive curvature if you go into the one part and the other part doesn't have a curvature at all, and some parts have a negative curvature. Okay. But the current conclusion is we are living here. Okay. The current conclusion is this. Okay. We don't have enough data to verify this. Okay. The current conclusion is that we are living on a flat earth. But I think it's a too simplistic assumption. Anyway, so what all this discussion is telling you is that this N map, okay, this normal map actually is a pretty interesting thing.